Hello friends, we already have learned about different representations of band structure in one dimension using nearly free electron model. In this lecture, we are going to learn about plotting the band structure in 2 dimension and 3 dimension. Let us start with 2D free electrons. Energy dispersion relation is E is equals to h cross square k square divided by 2m, where k is a 2D wave vector having 2 components kx and ky. Energy is a quadratic surface in k space given by E is equals to h cross square by 2m kx square plus ky square. Taking h cross square by 2m is equals to 1. I define energy in this line of the code. This is the code to plot the free electron energy in 2D. I take the range of kx from minus pi to plus pi. Similarly, range of ky is from minus pi to plus pi. This line is needed to plot a function on a 2D grid. I define the energy in this line and the energy surface is plotted in this line. Let us run the code. This is the EK diagram for 2D free electrons. Energy is a quadratic surface in 2D. However, it is more common to plot E versus K curves. For example, we can calculate energy along a specific direction, say kx direction. If we move along the kx line, then ky is equals to 0. And energy is given by E is equals to h cross square kx square divided by 2m. In that case, we get a curve which is similar to the case of 1D. However, in 2D, we can move along several directions like gamma to x, like gamma to y, like x to m, etc. We select some particular path like gamma to x, that is from this point to this point, then x to m, that is from x point to the m point, and finally m to gamma, that is from m point back to the gamma point. And we plot EK curves along these selected paths. Choice of path is not arbitrary but depends on symmetry. For example, in this case, energy along the gamma x path is the same as energy along the gamma y path. Thus, if we plot energy along gamma x, we need not plot energy along gamma y. Similarly, energy along ym path is same as energy along xm path. Thus, if we plot energy along xm path, we need not to plot energy along ym path. In other words, because of symmetry, gamma x and gamma y direction is equivalent. So, once we define gamma x, we need not to define gamma y direction separately. This is the code to plot the band structure along gamma x, m, gamma line. Energy is given by E equal to h cross square by 2m times kx square plus ky square. Taking h cross square by 2m to be equal to 1, we define the energy in this line. We have a user-defined function which returns the value of energy for a given value of kx and ky. To plot the EK diagram along gamma x, kx ky is varied from 0, 0 to pi by a 0. So gamma point is 0, 0, and this point is pi by a 0. In this portion, we vary kx, ky along the gamma x direction. Then we plot EK diagram along xm direction, where x is this point pi by a 0 and m is a point pi by a. In this portion, we vary k along the xm direction. Finally, we vary k in the m gamma direction in this portion of the code. This is the code to plot the band structure along gamma x m gamma direction. This is the user-defined function which returns the value of energy for a given value of kx and ky. This is where we vary kx, ky along the gamma x path and calculate energy along the gamma x path. This is where we vary kx, ky along the xm path and calculate energy along the xm path. This is where we vary kx, ky along the m gamma path and calculate energy along the m gamma path. Let us run the code. Energy is a quadratic surface in K space for 2D free electrons. We plot E versus K curves along certain paths. For example, in this case, we plot along gamma to x, that is the line joining gamma point and x point. Then from x to m, that is the line joining x point and m point. And finally from m to gamma, that is the line joining the m point and the gamma point. Gamma, x, m are high symmetry points in the first Brillouin zone of the reciprocal lattice of a square lattice. Thus, this is empty lattice approximation for free electrons in 2D because we are introducing reciprocal lattice in a free electron model. Note that K paths are confined to the first Brillouin zone. Because of symmetry, it is sufficient to plot EK curves along gamma to x to m to gamma. For example, EK curve along the gamma x direction is same as the EK curve along the gamma y direction. Thus, if we plot along gamma x, we do not need to plot along gamma y. Let me prove this to you. I write two codes. First one plots EK along the path gamma x m gamma. The second one plots EK along gamma y m gamma. In this code, we vary K along the gamma x path, whereas in the second code, we vary K along the gamma y path. Then we vary along xm and along ym. Finally, we vary K along m gamma and m gamma. The energy values are calculated in this user-defined function for a given value of kx and ky. This is the EK diagram for 2D free electrons plotted along gamma x m gamma. And this is the EK diagram for 2D free electrons plotted along gamma y m gamma. As mentioned previously, they are exactly the same because of symmetry. Thus, we can choose to show Ek along either gamma x or gamma y. We do not need to show both gamma to x and gamma to y. And this happens because x point and y point is equivalent because of the symmetry of the square lattice. Thus, if we show Ek diagram along gamma x, we need not to show Ek diagram along gamma y. Let us consider a case where energy dispersion relation is given by E is equals to h cross square by 2 times kx square by 4m plus ky square by m. Clearly, energy is not symmetric along kx and ky. Energy increases slowly in the kx direction and energy increases rapidly in the ky direction. How we can get such energy dispersion? Only way to justify such a dispersion is to assume that mass of electrons is 4 times heavier along kx. That is, we can write this as h cross square by 2 kx square by m plus ky square by small m, where m is the mass of electron along the kx direction and small m is the mass of electron along the ky direction, and capital M is 4 times the small m. Is this just a toy model? It turns out that such dispersion is indeed possible, and mass of electron is not constant in a solid. Mass of electron can be heavier or lighter compared to free electron mass along certain directions in a crystal. This is the Ek diagram along the high symmetry directions in the first Brillouin zone in case of anisotropy. Because of anisotropy, now gamma to x and gamma to y directions are not equivalent. Thus, we need to show Ek curve along x to gamma as well as gamma to y. Similarly, m to y and m to x are not equivalent because of anisotropy, and we have to show E versus k curves along m to x as well as m to y. Let us now plot the electronic band structure of free electrons in 3D using a Python code. The energy dispersion relation is E equal to h cross square by 2m times kx square plus ky square plus kz square. I set h cross square by 2m to be equal to 1 and then calculate the energy using a user-defined function in the code. For a given value of kx, ky, and kz, the function returns the value of energy. We have to plot energy versus k along gamma to x. This is known as the delta path. In the code, I vary k along the gamma x direction in this portion. Then we have to plot energy versus k along x to m. The line joining x to m is known as the set line. In the code, I vary k along xm direction in this portion. Then we have to plot energy versus k along m to gamma. The line joining m to gamma is known as the sigma line. I vary k along m to gamma in this portion of the code. This is followed by gamma to r and the line joining gamma and r is known as lambda. Finally, we plot E versus K along R to X, and the line joining R to X is known as the S line. This is the code to plot the band structure along gamma to X to M to gamma to R to X. This is the user-defined function where I calculate the value of energy for a given value of Kx, Ky, and Kz. This is where I vary K along the gamma X line and calculate energy along the gamma X line. This is where I vary K along the XM line and calculate energy along the XM line. This is followed by M gamma, gamma R, and Rx. Let us run the code. This is the band structure of 3D free electrons plotted along gamma to X, X to M, M to gamma, gamma to R, and R to X. Note that gamma, X, M, and R are high symmetry points in the first Brillouin zone of the reciprocal lattice of a simple cubic lattice. We are using reciprocal lattice in case of free electrons, and this is known as the empty lattice approximation. K paths are confined within the first Brillouin zone. Because of symmetry, it is sufficient to plot energy versus K along gamma to X, X to M, M to gamma, gamma to R, and R to X. I have skipped energy versus K plot along R to M path, and this is left as an exercise for you. So far, we have plotted only one band in the EK diagram using Python code. However, in case of 1D, we have seen that all the bands are plotted in the first Brillouin zone in case of reduced zone scheme. How do we do it for higher dimension? For example, take the case of 2D. We have plotted the band structure along gamma to X, X to M, and M to gamma, shown by the red lines in this diagram. If we keep going along gamma X, then we reach a point gamma plus G, and finally reach a point X plus G, which is outside the first Brillouin zone. How do we map the EK curves in these zones to the first Brillouin zone? Similarly, if we keep moving along gamma M, then we reach a point gamma plus G dashed, and if we keep moving along XM, then we reach a point X plus G2 dashed, and if we keep moving along this line, then we reach a point gamma plus G2 dashed. How do we map the EK curves along these lines to the first Brillouin zone? Let us learn that. In this diagram, red lines are the actual E versus K curves we obtained from our code. Let us start at this gamma point. We draw a parabola which fits the red line along the gamma X direction. The black region is the portion which is lying outside the first Brillouin zone. We have to bring it inside the first Brillouin zone. Next, we draw a curve that fits the actual E versus K curve in the XM region. Now, this black portion is lying outside the first Brillouin zone, and we have to bring it inside the first Brillouin zone. Then we focus on the other gamma point and draw a parabola that fits the actual EK curve along the gamma M direction. Now, this black region lies outside the first Brillouin zone, and we have to bring it inside the first Brillouin zone. If we keep moving along the gamma X direction, ultimately we reach another reciprocal lattice point. Here, we draw a E versus K parabola at this reciprocal lattice point. And this black portion of the parabola, we bring it inside the first Brillouin zone. We can keep doing this and bring all the EK curves lying outside the first Brillouin zone to inside the first Brillouin zone. This is the E versus K diagram for 2D free electrons in reduced zone scheme. The red portion of the curves are energy for K paths within the first Brillouin zone. The dark blue portion is the energy along X to gamma plus G. The green portion is energy along gamma plus G to X plus G. The magenta portion is energy along M to X plus G two dashed. The black portion is energy along M to gamma plus G dashed. And finally, the light blue portion is energy along M to gamma plus G two dashed. Let us try to understand how good is empty lattice approximation. Does it work for metals where valence electrons are like free electrons, or does the periodic potential have very significant effect in case of metals also? Most of the metals we know are either body-centered cubic like iron, or face-centered cubic like aluminium, copper, or hexagonal close packed like cobalt and titanium. Unit cell of face-centered cubic lattice and corresponding first Brillouin zone and high symmetry points are shown in the diagram. Let us plot empty lattice band structure along L to gamma to X to U to gamma and compare with actual band structure of aluminium. In case of a square lattice, I showed you how to plot the band structure using empty lattice approximation. We can use the same principle and do it for a face-centered cubic lattice. Obviously, doing it for a face-centered cubic lattice is going to be much more complicated than a square lattice. So, I am going to just show the result. The first diagram from the left-hand side shows the empty lattice approximation for a face-centered cubic lattice. You can find the empty lattice band structure for different lattice in this website. In the right-hand side diagram, I show the actual electronic band structure of aluminium. I calculated this using ab initio package quantum espresso. Details of the calculation is beyond the scope of this course. So let us just focus on the plot. Comparing the empty lattice and actual band structure, we find good qualitative match. Periodic potential definitely has some effect, but still the overall agreement is very good. In conclusion, for metals like aluminium, nearly free electron model works very well. The weak periodic potential indeed modifies the empty lattice band structure to some extent, but the overall agreement is very good.